So in this video, we're going to look at how to do polynomial interpolation with Matlab. We covered the mathematics of this method in a video just not too long ago. So today here we're going to actually program this and plot the result of it. So we're going to start here by looking at this section. We're going to create a random vector, right? There's a Matlab function called rand, and this creates a vector of size n. Here we're setting n to be 6, so this will just be random numbers. So this will be our data. It will be given at the grid from 1 to n, in this case 1 to 6, and there'll be 6 numbers chosen randomly associated with each of these points in the grid. And if we run this, so we can run this section, we can see here are our points, right? And we have 1, 2, 3, 4, 5, and 6. And the function f, or the vector f evaluated this grid points, are marked here in red. But you can notice that we only have these measurements at the exact grid locations. If we inquire the value of this vector at, or this function at, for example, coordinate 1.5, we don't have it. So we're going to now produce a curve that passes through all of these points, and that this will be a function that also allows us to evaluate this function anywhere we would like. We're going to again assume that we are going to fit a polynomial model through all these points, and we're going to do this by setting up as a linear system and solving it. So first thing we need to do is create the system matrix, or that matrix A in our previous videos. And here's a code that says we're going to go up to degree n-1, right? So we're going to essentially fit a 5th order polynomial on these 6 points. And so we're going to loop from 1 through d, and we're going to create this vector which I'm calling phi, right? We also called it phi in our previous lecture. And we're going to evaluate this phi vector and concatenate. So we're going to build this matrix essentially column by column by concatenating the right phi vectors at the right time. So here is our system matrix, and then once we have the system matrix and we have our data f, we simply solve for AC equals f, right? And here's the backslash operator, which uses something akin to Gaussian elimination in Matlab to solve the system, right? So let's do this. So let's create, we already created this, so I can see this because we have this value in the workspace here, showing what's there. So we can just move on and evaluate this cell here. So now we have created this matrix A, and A is a 6 by 6 matrix, so that's all correct. And now we're going to solve for these coefficients, right? So now we also have this vector C, which is also a 6 by 1, and you can see the C is a complicated vector with many numbers in it. And now we're going to check that everything worked well. We're going to evaluate actually our matrix A applied to C and obtain this vector which I call temporary f, and then I'm going to compute the error between my original f and my temporary f, and I'm going to display the maximum error that I will obtain here. The point here is I want to make sure that my f that I compute this way is equal to the f that I was given. So let's run the section, and we can see that the maximum absolute value of the error between the initial point and the interpolated point is something to 10 to the minus 14. So this is really good, because the worst possible error in this case that Matlab could produce, given that it's using digital computation, is something like 10 to the minus 16. So we are making some errors here, but they're very, 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 very minor, right? There, I have to say 14 varies to express how minor they are in relation to the numbers that are being given here. So so now we can go ahead and plot the value of this polynomial throughout all the coordinates x here, and you can see that we have plot these values very nicely. But perhaps because I plotted one by one and I closed the previous figure, you can't see the whole the points superimposed on this curve. So let me rerun this whole script again, and then you will be able to see this method's plot, right? So here are the initial data points, and these are points in red. And the blue curve that we're plotting here is this Matlab linear interpolation curve that we just plot. Ignore this red curve, which is the one that I called the Matlab function with, just to show you that this can be done with a standard Matlab function. This blue curve is this fifth order polynomial that is passing through all of these 6 points, right? And you can see it's a pretty smooth curve, as you would expect from a fifth order polynomial. And you can see that this polynomial passes exactly through the points, right? So let's cover how we evaluated this. So we had to compute this function. We had to make this function polynomial n, or poly n, which I called poly n, and this here you can see the code of this function here, right? It takes in the x coordinates and that you would like to interpolate and see, and you know the degree of the interpolation polynomial, so you can go from 0 to n and sum this result this way, and you then evaluate this polynomial that way. So and here is the call to produce this polynomial, right? And I went ahead and also plot, so you don't have to code all of this yourself, although in the homework we'll ask you to do that. But you can also use Matlab's interpolation function. It's called interp1, and here's an example how to call. I encourage you to pull up the help file for this particular function. You pass in the independent variable, the dependent variable, or the data given, your f, and then you pass the values that you would like to interpolate this f at, right? And you can choose the method. There is linear, quadratic, cubic, and so on. Then these are all piecewise linear, right? So, and here's the legend for this. So let's run this whole entire script once more, and you can see what's going on here again in this figure. You can see this red curve here is essentially building a line between these any two consecutive points, and that's very different from the cubic fifth order polynomial that we're plotting, right? So they're all guesses, and at the moment we haven't said anything much more than they're just guesses. We don't know which one is right or wrong because we were not given more information in the problem. So anyway, the script is available. You can go ahead here and change the number of points you would like to do. If you would like to do 8 points, for example, make sure you save it, and then you can run the whole script, and now you should have the same thing going through 8 points, right? If you would like to do 2 or 3 points, you could also do the same.